In the previous video, in the previous exercise, we looked at how to do this MNIST manual written digits classification problem by using a normal, dense, fully connected neural network, right? But at that time, we mentioned that there's a possibility for improvement by taking into account the so-called neighborhood information. So this kind of a neighborhood information is actually quite important uh, for this kind of image data, right? So if you look at one of those digits, say this is a 4, right? So if you look at the images, uh, it's a grayscale image first, right? So it's made up of grayscale values, right? So uh, exact black is going to be like a 0, exact white is going to be like 256 or 255, right? So um, how do people actually recognize this is actually number 4, right? It's actually the arrangement of those white pixels, right? The arrangement of those white pixels. So if you look at this, for example, this particular vertical stroke, right? This is like a vertical line. How do we know it's a vertical line, right? Because of the neighborhood information, right? So if you look at this one particular pixel, to the left and to the right, it's all black, right? And then look at the pixel right below it, it's still white, and then you have black to the left, black to the right, right? So we know this is a vertical strike, right? So this kind of neighborhood information is kind of important for humans to recognize what kind of a pattern those pixels actually form, right? When we did our fully connected dense multi-layer perception neural network, we actually flattened out this kind of two-dimensional image into like a one-dimensional array, right? So that's an operation that's going to destroy this kind of neighborhood information, right? So pixels that are right next to each other, right? For example, this pixel and the pixel right below it, right? Those are right next to each other, right? This kind of neighborhood information is lost when we're doing this kind of flattening, right? So the pixel right below this kind of this white pixel could be, instead of right next to this white pixel, it's going to be like located a number of pixels away, right? Once you flatten it, right? So this kind of a neighborhood information is important for humans to recognize a particular pattern, especially in this kind of two-dimensional images. And if we can actually build this kind of a neighborhood information into our neural network, then it's gonna be advantageous for the neural network to recognize this kind of a neighborhood or this kind of spatial pattern more easily, right? So how do we actually do that, right? How do we actually do that? Conceptually, it's not really that difficult because in our multi-layer perception neural network, the input layer is pretty much just a one-dimensional arrangement of all the neurons, right? So if the pixel number is 28 by 28, then it's the number of neurons in the input layer is going to be 28 times 28, right? It's like 700 something, right? So, but there is no specific reason for us to actually arrange all those input neurons in a one-dimensional array, right? It's not really that kind of a um, it's not really required for us to actually arrange all those input neurons in this kind of one-dimensional fashion, right? We could just arrange our input neurons in a way that's kind of adapted to this kind of two-dimensional pattern, right? So suppose we do this kind of thing. We do this kind of thing. So this is our input image that's displayed in this kind of a three-dimensional fashion, right? So you can think of it, each of the zeros and the ones can be sort of as the grayscale value, right? So if you normalize the grayscale value, it could be a value, it could be a floating point value that varies between 0 and 1, right? So that could be our input neuron. So each of the pixel is just going to be an input neuron, right? That's going to spit out the exact grayscale value for that particular pixel, right? So we could just arrange our input neuron in this kind of two-dimensional way, right? Then what about the neuron that's going to be above, or that's above the input layer, right? That our input layer is now, our input neuron layer is going to be this kind of two-dimensional layer now. So what's going to be the neuron that's going to be above it, right? So how do we actually deal with that? So the neurons that's going to be above it is still going to be arranged in a two-dimensional fashion. It's still going to be a two-dimensional fashion. So every neuron that's in the upper layer is going to have a connection. Is going to have a connection with a rectangular domain, or this kind of a square domain of the input neuron, right? So for the upper layer for the upper layer neuron, it's going to have connections. It's going to have arrows that's going to go from each of the pixel within this particular box to this upper layer neuron, right? To this layer neuron. So what about the weights of those of those connections, right? So in this particular depiction of a conventional CNN convolutional neural network, the terminology is a little bit different from what we have talked about so far, right? So you're gonna see terminology called filter. What exactly is a filter, right? A filter is exactly the weights, but it's arranged inside in this kind of a matrix, this kind of two-dimensional matrix way, right? So the connection from this particular pixel, say 1, to the upper layer neuron is going to have a weight that's 0, right? Of course, this weight is sort of assumed weight. We are doing a forward pass here, right? When we are actually doing the back propagation, all those weights are going to be adjusted later on, right? During this optimization process. And this pixel is going to be connected to the upper neuron with a weight that's 2, right? And this pixel is going to connect it to the upper neuron with a weight of 1. So in the CNN terminology, this filter is basically a matrix of all the weights that's going to be used for connecting those input neurons to the upper neuron, right? And then what's going to be the output of this upper neuron, right? So the logit of the upper neuron is going to be a weighted summation of all the input neurons, right? But this weighted summation is going to be a summation over what kind of a region, right? It's going to be a weighted summation of this particular rectangular region. So it's going to be this input neuron multiply this weight plus 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 this input neuron multiply this weight, and then goes on, right? So this summation is not going to be just like a one-dimensional summation anymore. It's still a one-dimensional summation, but it's a one-dimensional summation over this kind of two-dimensional region, right? With the weights that's exactly going to be given by this particular filter, right? And sometimes people call this filter the numbers inside of this two-dimensional filter a kernel, right? But it's pretty much means the same thing, but it's the weights, right? The values of the kernel is actually the weights that we have to optimize later on once we start training, right? So the logit is going to be the weighted summation of all the input neurons inside of this rectangular region with the weights given by the filter, right? That's going to be the logit. So the definition of logit is not really any different from the previous exercise that we have done, or our introduction of the fundamentals of the neural networks, right? So the logit's definition is the same, right? And then what's going to be the activation function, right? What's going to be the activation function? So the logit is going to be used as the input to the activation function. So what's going to be our activation function? Again, all those activation functions that we have talked about so far, the sigmoid, right? The tangent edge, the ReLU, right? All those kind of activation functions are available, right? You can choose whatever you want based upon the specific problem at hand. And in this particular exercise, we are going to use the ReLU activation function. So the logits that's computed in this particular way is going to be used as the input to our ReLU activation function, and then it's going to spit out an output, right? And that output is going to be a single number. What's going to be the single number? That's the single number, right? That's a single number. Right, that's going to be the output of that upper layer neuron, right? And then what are you going to do, right? What are you going to do? Because this is just a very small portion of the entire image, right? This is just a 3x3 portion, sub-image of the entire image. The entire image is like 28 by 28. You're doing it like a 3x3, very small chunk of that big image, right? So you are just capturing a very small portion of a very big image. So how do you actually how are you gonna sort of go through the entire image, right? So the way that we do this thing in CNN or convolutional neural network is that we move this particular kernel uh, sort of both horizontally and then vertically throughout the entire image with some kind of stride, right? Whatever the stride might be, you can specify it, right? Usually it's just going to be one. So if it's a 3 by 3 square, right? So if you actually move it move this way, move the kernel this way, right? Then the next image is going to be shifted by 1, right? And then you're going to use exactly the same weights, right? Exactly the same weights to produce another output, and that output is going to be located over here, right? So as you actually move this kernel or move this filter throughout the entire image, your output for that particular filter is going to be another two-dimensional matrix. That's just like a image, right? And that image is called a feature map, right? Every time we talk about feature map, it is with respect to a specific kernel or a specific filter, right? So for this particular example, we only have 9 weights, right? And what I was saying that these 9 weights doesn't change as you actually move across the entire image, right? So it's the same 9 weights that's going to be used for every kind of a shift, right? For every stride, both horizontally and vertically, right? That just gives you 9 degrees of freedom, right? If you consider one biased term, so this is the weighted summation, right? And then usually you have to consider a biased term, right? A biased term is just another number, so it's just 10 degrees of freedom, right? You only have like 10 degrees of freedom in this particular in constructing this particular feature map, right? So how do you actually introduce more degrees of freedom, right? You use more feature maps. You use more feature maps. You use more filters. You use more filters, right? So you can actually switch to another different kind of a filter that's going to be composed of another set of weights or another set of filter numbers, right? So suppose another 3 by 3 filter, right? That's going to give you 9 more weights, right? Again, those 9 more weights together with bias, that's another 10 degrees of freedom, right? You can construct another feature map, right? Doing exactly the same operation, that's going to produce another feature map that's corresponding to the second filter that you have introduced, right? So by introducing more of those kind of filters or kernels, you can construct more feature maps and introduce more degrees of freedom that's going to allow you to actually optimize your neural network, right? To fit the labels, right? So this is called a convolutional layer. For every convolutional layer, you get to specify how many filters you're going to want, right? And then for each of the filter, what's going to be the dimension? Is it going to be 3 by 3, or is it going to be 2 by 2, or is it going to be 4 by 4, right? And also you get to specify what's going to be the activation function, and we're going to use the railway activation function, right? And that's called a conv layer, and it's going to be a two-dimensional conv layer inside of the using the Keras library, right? But the basic idea is pretty much the same as what we talked about in the fundamentals of neural networks, except that now the arrangement of those neurons is not going to be a one-dimensional thing. It's going to be a two-dimensional arrangement of the neurons, right? And then it's not going to be fully connected, right? So for each of the upper layer neuron, the connection is just within this field of perception, right? Right. So when you're actually computing one output, right, those neurons, those input neurons lying outside of the reception field is not going to be connected to the output, right? There's no way to actually connect them to the logit, right? Because there's no connections or arrows that's connecting the upper layer neuron to the input neuron, right? So it's not going to be fully connected, right? It's not going to be fully connected. But it's okay. It's okay. And once you have enough of those filters or enough feature maps, you still can introduce a sufficient number of degrees of freedom, right? And this kind of and what we were talking about is that the number of degree freedoms is not sort of the more the better. It's not like that, because if you have too many number of degrees of freedom, suppose it's actually fully connected, right? You could have a overfitting problem, right? Then you have to overcome it, right? And the CNN gives you this kind of a compromise, or this kind of trade-off that um, gives you the degrees of freedom that's kind of useful to account for this kind of neighborhood information, right? So if you look at all the neurons that's kind of arranged within this kind of a receptive field, it's all neighboring each other, right? It's not like you take one pixel over here and then you take another pixel over there. It's not like that, right? They have this kind of neighborhood information that's preserved during this kind of calculation, right? So it's always for a certain neighborhood or certain region that you're actually doing this kind of weighted summation to get the logits, right? So that's a conv layer, right? And another layer that we have to consider is called the pooling layer, right? Usually the output is going to have similar dimensions as the input if we use this kind of a stride of 1, right? It's going to be smaller image, but the dimension is not going to be much smaller, right? So if you have a stride of 1 for 28 by 28 image, one feature map is going to be like how much? Maybe like 26 by 26, right? If you don't do any kind of padding to make the input image kind of bigger, then it's going to be 26 by 26 because it's your filter is like 3 by 3, right? But it's still going to be a big image, and this kind of big image is it needs to be subsampled, and this is done through this called pooling layer, right? And this pooling layer doesn't actually introduce any degrees of freedom because you don't have weights that's introduced in here, right? So for a but this kind of pooling is done still in the fashion of accounting for the neighborhood. So suppose you are doing a 2 by 2 pooling layer. So that means just you're just going to take a square, take this kind of 2 by 2 square in the feature map, and then look at what's going to be the number that's maximum inside of this 4 by 4 2 by 2 small matrix, right? If the number is 8, right, this is the maximum, then you just take that number and then map it over to the output of this pooling layer. And here we are actually doing a max pooling, right? We're taking the maximum value in this 2 by 2 square region, right? And then we'll take the maximum value and then map it to the output, right? Sometimes people do averaging, right? So if it's a 2 by 2 pooling, then you can just average these 4 numbers, right? The average number is going to be the output. Sometimes people do min pooling, right? But in our case, we don't want to do min pooling. We don't want to do max pooling, right? Because we care about the feature, we care about the most significant grayscale, right? The grayscale actually tells us what's going to be the pattern, right? So, and that's a pooling layer, right? Usually followed by this kind of conv layer and a pooling layer. You have another conv layer and then another pooling layer, and then you can actually stack as many conv layers and pooling layers as you want, right? But without introducing too much of a degrees of freedom to overfit the problem, right? And then eventually, if you are doing a classification problem, usually you have a output layer that's kind of fully connected, right? And then depending upon how many classes there you are actually classifying, the number of neurons in the output layer can be determined based upon the class number, right? And then usually it's a softmax layer, right? And in the output layer, it's going to be a fully connected layer. It's you have to do a flattening of the two-dimensional feature maps, and then doing this kind of output, right? So one of the things that people have to pay attention to is for this kind of diagram, usually you only consider this kind of two-dimensional thing, right? But usually you have colored images, right? So for our example, it's just going to be one color, right? It's grayscale. But usually colored images is going to have like 3 different colors, R, G, and B, right? Red, blue, and green, right? That's going to give you not just a one two-dimensional matrix. It's going to give you like 3 two-dimensional matrix. And what I was saying is that every time you change to a different filter, it's going to generate a new feature map, right? So for all the outputs of the conv layers, it's not going to be a single two-dimensional matrix. It's going to be like a stack of multiples of two-dimensional images, right? So in practice, what you're actually doing the weighted summation on is not really a one-dimensional thing. It's actually a three-dimensional thing, right? It's a three-dimensional thing. You have to consider the other axis, and this axis is usually called the channel axis, right? So for the input image, the different channels are going to correspond to the different colors, R, G, and B, right? And then for the intermediate layers, the outputs of each of the conv layer, the channels are going to be corresponding to each of the different filters or different kernels, right? Each filter is going to generate a two-dimensional feature map, right? So the channels, the number of channels are going to be the same as the number of filters you are going to use, right? So this kind of two-dimensional diagram sometimes are kind of misleading, but it's in practice, because in practice we're actually doing this kind of three-dimensional calculation, right? Because you have to consider a channel side, right? So the channel dimension, right? So the channel dimension is going to be like another dimension, right? So it's not really a two-dimensional matrix multiplied with a two-dimensional matrix element-wise, right? It's more like a two-dimensional matrix. No, it's like more like a three-dimensional kind of a thing, element-wise multiply with a three-dimensional thing, right? So that's gonna give you like one single output. Yeah, but now let's write some code, right? So that's sort of the basic concept. We're gonna come back to it when we write the code and construct the model. The code is not too difficult. It's lots of the code is actually similar to the ones that we did last time, especially for importing the data, right? So we're gonna import the NumPy from TensorFlow. Import keras, and then from TensorFlow dot keras import layers, right? That's all the libraries we're going to use, right? So the first thing we're going to do is still to load the data, right? Xtrain, Ytrain, and then Xtest, Ytest is going to equal to keras.m dataset .mnist dot load data, right? And because we are not going to save the data on local disk, so we're just going to download it, right? So by default, you can actually, if you don't give any input over here, then it's just going to download the data from the web. If you have a local copy of the entire dataset, you can actually specify the path to that dataset in this parenthesis, right? And then number of classes. It's going to be 10 classes. That's the number of that's going to be the number of neurons in the output layer, right? And then what's going to be the input shape, right? It's going to be 28 by 28, right? But don't forget that we are going to do because this is a grayscale image, right? So the channel number is actually 1, right? But for three-dimensional, for colored image, the channel number is going to be 3, right? Because you have RGB, that's going to be 3 input matrices. So here we have to specify the dimension of the input shape, right? And Xtrain, let's normalize the data first. Float 32, and then let's just divide it by 255, right? That's going to normalize the pixel values from 0 to 255 to a floating point number between 0 and 1, right? So, and then Xtest, we're going to do the same thing. Xtest as type float 32 divided by 255, right? And then one of the things that we have to pay attention to is about the dimensions, right? So here it's a three-dimensional thing, right? With a channel number that's channel dimension with a 1. But here it's going to be a two-dimensional thing, right? It's going to be 28 by 28. So how do we actually extend it to a third dimension, right? To a three-dimensional thing with the third dimension given by 1, right? And it's actually NumPy actually provides this kind of a functionality. So mp.expand dims, right? And then it's going to be, the first input is still going to be Xtrain. The last input, we're going to give it -1, which means that we are going to let NumPy to determine what's going to be the dimension that we want to expand, right? By default, it's going to expand it to the one dimension for the last dimension, right? So it's going to change it to 28 by 28 by 1, right? And then Xtest is going to be mp.expand dims X test, and then -1. Right, so that's sort of the preparation work that we need to do for the input images, right? So what's going to be the y, what's going to be the label, right? For now, the label is not really in this kind of one-hot encoding format. We are going to do the same kind of thing that we did last time. We're going to use uh, this time we're going to use keras.utils.to categorical, right? And then ytrain num classes, right? That's going to convert it into this kind of one-hot encoding, right? And then y test is going to equal to keras.utils.to categorical y test and then classes, right? So that's all the preparation that we need to do for the labels, right? And that's pretty much all the preparation, all the data kind of preparation that we need to do. So now let's construct our CNN model, right? So we can, last time we were writing the model and construct the model one layer at a time, right? So this time we can do this thing, keras.sequential, right? We can actually put the entire model into just this pair of square brackets. So this particular function, this sequential function, allows us to actually give it some kind of list as the input, and this list is composed of all the different layers, right? The first layer is going to be the input layer, and Keras actually has the input layer for us, right? And then the shape is going to equal to input shape, right? That's going to be our first input layer, and then we can actually add those conv layers and the pooling layers one layer at a time. So first we are going to add a conv layer. So this conv layer is inside of this layers sublibrary, right? So layers.conv layer. It's going to be a conv2D. We're going to do a two-dimensional conv layer. And then for the first layer, we're going to use 32 filters. You can try different values, right? I found this value to be relatively good. And then the size of the filter is going to be 3 by 3. And then the activation function, it's going to be relu, right? And then that's our first conv layer, right? So corresponding to this particular figure, so each of the filter, each of the kernel is going to have a 3 by 3, this kind of a matrix, right? 3 by 3 matrix, two-dimensional matrix, right? And then we're going to have like 32 of those kind of filters, right? So you can imagine it's going to be like a 32 weights. It's going to be like a 9 weights, right? 9 weights plus 1 bias. That's going to be 10 degrees of freedom, right? And then you're going to have like 32 of them, right? For 10 degrees of freedom for each filter, and then you have 32 filters. So it's going to be like 320 degrees of freedom for this particular layer, right? And the activation function is going to be relu, right? So once you have done this kind of a weighted summation using the weights, right, together with the input values, right, that's going to give you the logits, right? The logits is going to go through that relu function, which is just a flat part, and then have a linear trend that goes 45 degrees, right? That's going to be the first conv layer, right? And then what are we going to do is to add the pooling layer. So layers dot max pooling. So we're going to take the maximum value. It's going to be still 2D, right? And then the pool size is going to equal to 2 by 2, just like what's shown in the image, right? Right. So for the subsampling or the max pooling layer, we're going to take like 2 by 2 pixel, 2 by 2 output, this kind of 4-number subregion, and then take the maximum and then map it to the output of the max pooling layer, right? That's one conv layer and one max pooling layer, right? And let's try to add one more conv layer. But this time we're going to use 64 filters, right? And then kernel size, it's still going to be 3 by 3. And then activation is still going to be relu. Right? And then layer max pooling 2D pool size is gonna equal to 2 by 2, right? Um, yeah, that's pretty much all the convent pooling layers that we are gonna add, right? So once we are done with that, we can actually do a layer flatten. So because our output layer is going to be like this kind of one-dimensional thing, so eventually we still need to actually flatten all those two-dimensional things or three-dimensional things into like a one-dimensional thing, and then to have a fully connected layer, right? So, but at this point we can add some kind of a dropout. Let's just give like 0.5, right? So this is going to help us to actually reduce overfitting. And then layers.dense, that's the output layer, right? It's going to be a fully connected layer. Num classes, that's going to be the number of neurons in the output layer, and then activation is going to equal to softmax. We talked about softmax in our in our previous exercise, right? So, and that's going to be the entire model, right? Okay, so our model is done, right? So what we can do is to print out the summary, model.summary, right? And then now we can actually start training. And this kind of training process is actually identical, exactly the same as what we did in our previous exercise. So we have to specify the batch size. So we're going to take 128. And then epochs, let's give it like 15 epochs, right? Before we actually train the model, we have to compile the model first, right? Model.compile. And at this stage, we can actually specify what's going to be our loss function. We're going to be cat go recall cross entropy cross entropy. We talked about the categorical cross entropy last time in the last exercise. The optimizer, we're going to use the same optimizer as we used last time. It's Adam, right? And then metrics, it's going to be accuracy, right? And then model.fit, right? X train, Y train, batch size equals to batch size, and then epochs equals to epochs. And then for each of the iteration, we're going to have a validation split, which means that for the training data, we're going to split the training data into two parts, right? About 10% are going to be used for validation, right? The process of validation is similar to what we did with cross-validation when we were doing that regression problem, right? But it's automatic here. We don't really have to actually manually separate the entire training data set into like two parts, right? So as long as you have specified this kind of validation split, it's going to automatically set aside 10% of the training data, use it for validation. And this kind of validation split is going to be done randomly, right? And then it's automatic. You don't have to do anything. So that's the nice thing. And then once we are done with the training, we can do evaluation, right? So score is going to equal to model.evaluate. We're going to use the test data and then y test, then variables is going to equal to 0. And then all we have to do is to print test accuracy. And it's going to be the second number inside of the output score. Right, second number is score 1. Right. Okay, so let's just run it. Looks like I have a problem, right? But let me pause the video and try to debug a little bit and see if I can discover where the problem is. Okay, so I had a typo, right? It's supposed to be shape, shape instead of I typed it wrong. It's I typed it as SAHPE or something. All right, now let's run it again. It looks like I got another error. Okay, I think that's another typo. It's not soft wax, it's supposed to be soft max, right? and then let me run it. Okay, looks like it has started running now. So on my laptop, on my desktop, it's gonna take a while to actually train this model because we have to go through 15 airports. So I'm gonna pause the video and we'll come back. Now we have finished training and also evaluation, and the test result is 99.15 or close to 99.2% of accuracy on the testing data. So last time when we used the multi-layer perceptron, that's like a dense neural network, we using like a dropout as a regularization, we reached a accuracy that's 98.1 something, right? Close to like 98.2%, right? So by changing to convolutional neural network and accounting for the kind of neighborhood information or the proximity of different pixels, it's by using this kind of a convolutional neural network, we have improved our accuracy by close to like 1%, right? Looks like a very small number, but when you apply it in practice, on millions and millions of input data, it could be like the difference could be significant, right? Could make the entire application usable or not usable, right? So it's actually worthwhile to actually think more carefully about what kind of structure of the neural network that you want to adopt, right? For this kind of image-related problems, convolutional neural networks is a kind of a very useful, right? It's a very useful construct. Here we have looked at 2D convnet, right? So sometimes when you are dealing with one-dimensional data, one-dimensional convnet could be useful, right? In many of the scientific applications, the data are coming from sensors that are distributed more or less randomly throughout the space, right? And each of the sensor records signals as a function of time, right? And in that kind of case, those kind of one-dimensional convolutional could be useful for you to actually analyze those time signals, right? So this is going to be the last exercise of the entire semester. It's going to be the end of the course, and what I hope is that this is not the end of your journey of mastering the art of machine learning. It's a powerful technology, and it's going to transform the world, for better or for worse, depending upon if we understand it.